All right, so let's move on ahead. And I've talked a lot about colliding galaxies in the past because this is how galaxies grow over time. And so in this story, this is a new paper that just came out where the authors investigated the mass of the Andromeda galaxy. The Andromeda galaxy is the closest large galaxy to our own Milky Way, so it's very similar roughly similar in size, but there's been a lot of dispute about exactly how massive it is. And so our Milky Way is anywhere from 600 billion to over, so there are some estimates that place it over 1 trillion solar masses. But the Andromeda galaxy, the numbers have ranged from 800 billion to 2 or 3 times that. And so this was a paper that looked at a new technique for trying to identify, really nail down the mass. And what they find is right at around 800 billion solar masses. But what's kind of cool is that, I mean, I think the paper is really cool, but I think what's really neat for the public is that they also tried to run a computer simulation to show what a collision or a merger between our Milky Way and the Andromeda would look like. So this is something that is supposed to happen in another 4 or 5 billion years. And these types of collisions or mergers take place all the time, and our Milky Way has probably gone through lots of mergers over its history since the beginning of the universe. But this is probably the largest merger in the Milky Way's history. And so we'll just run through this animation. And you might worry that, well, if 2 galaxies merge and collide, what will happen to the stars? Well, it turns out that there's enough space in between all the stars and our 2 galaxies that these merger scenarios can take place over billions of years, and not a single pair of stars will get close enough to collide. And that's just because there's so much space in between the stars. So what we're seeing is, I believe it said the blue was the gas. Is that right? Okay. And the red was, I think, the stars. I don't think, first I wasn't paying attention to the beginning of the video. So we have 2 spiral galaxies, and so spiral galaxies are distinguished by their disks, which are the pizza-shaped part of the galaxies, and they consist mostly of gas. And what's interesting is that this gas provides the raw material for formation of the next generation of stars. And so what you'll see is that in the aftermath of this initial collision, gas gets crammed together, and it actually generates lots of new star formation. And so you see lots of red material, or those red dots, which represent new stars, and the gas slowly gets used up. And also a lot of the gas gets dispersed back into the intergalactic medium. And so in the end, what happens is when you have a merger of 2 spiral galaxies, you actually get what's known as an elliptical galaxy, where you don't have very much gas, or the gas disk is much smaller, and you have what's left over is mostly stars. All right, so there's that. And what I'm going to do is we're moving from close to home to subsequently larger and larger distances. And so the next topic is another computer simulation, but this is over a much, much larger region of space. And so this is about the Illustrus simulation, which is a collaboration between 2 different groups in Germany, the Max Planck Institute for Astronomy in Heidelberg, and then the one for astrophysics in Garching, Germany, and then also scientists at Harvard and at MIT. And they've been working for many years on these computer simulations, and so they recently announced Illustrus, the next generation, or Illustrus TNG. And before I jump into the simulation results, I want to just lay out what the makeup of our universe is. And so it turns out that if we look at if we pretend this pyramid, which you're probably familiar with, represents all of the ordinary matter in our universe, it turns out that, well, most of the matter in the universe is made up of hydrogen and helium, on the order of about 99%. But much of it is dark, meaning it's not lit up, so it's really hard to detect. So the visible atoms are up here at the top, so they make up a small fraction of all of the ordinary matter. So this is matter that consists of protons and neutrons and electrons, things that you learned make up matter in school when you were in chemistry class, for instance. But it turns out that in the last century, we've discovered that the universe is more bizarre than we've ever imagined. And that's because, well, here we go. Sorry, I got confused. Here are the invisible atoms, and then here is the visible atoms, and hydrogen and helium make up 0.5%, and all atoms heavier than hydrogen and helium is only 0.01%, and then the invisible atoms make up about 4%. I got ahead of myself there. But what really dominates matter-wise is something called cold dark matter. And this is something that we've had observational evidence for about a century, but people still don't know what this cold dark matter is. It's still under intense speculation, and astrophysicists, cosmologists, particle physicists are all working on trying to figure what this stuff could be. But that it makes up about 25% of all of the matter energy in the universe. And then finally, the really bizarre stuff is dark energy, which causes the universe to expand faster and faster. And even though we have a name for it, dark energy doesn't have anything to do with dark matter. And dark energy is even more mysterious than dark matter because it was never predicted before it was discovered. And we'll see towards the end a little bit more about dark energy and dark matter. But so in order to simulate the universe, you actually have to incorporate all these elements. So not just ordinary matter, but dark matter and dark energy as well. And so what they do is when they run these computer simulations in supercomputers, they define a big box, a volume that they want to simulate what will happen. And so under different simulations, there's TNG 50, 100, and 300. They've gone to bigger and bigger boxes. So they're looking at larger and larger volumes of space. And 300, this is megaparsecs, so that's on the order of about 1 billion light years. There's about roughly 3.25 parsecs in a light year. And so it's just under 1 billion light years. And what they do is they can't, for something this big, and they're trying to run a simulation from the beginning of the universe all the way to today, they can't have, they have to fill this volume with particles that represent matter and dark matter. And right now, the smallest particle that they have, it represents an object with a mass of about 100,000 solar masses for ordinary matter, and then something slightly larger for dark matter. So you can see that this is still very much an approximation, just because we're not modeling down all the way to the masses of stars, which are roughly about the size of the sun. But it can still give you a pretty good gross idea of what happens when matter evolves over the course of the universe. And so for this recent press release, they showed, for instance, what the ordinary matter or baryonic matter looks like. And you can see this kind of cosmic web where material has fallen into the centers where the dark matter is densest. And so these are the locations of giant clusters of galaxies. And so you see more clusters here and here. And material is literally streaming in and falling in. And as a result, you also get these giant voids that open up as material empties out of the voids and they fall into the clusters. And what's really interesting is that when we go out and observe space and map galaxies and galaxy clusters, we more or less tend to find them clumped up in this sort of hierarchical arrangements that we see in these simulations. And so by comparing the computer simulations to what we can observe, we can, we know that these computer simulations, even with the approximations that they have, they do a pretty decent job of simulating what is happening in our own universe. So here is another shot from their simulations, where in this case they're showing the dark matter, and then they're also showing some of the collisions between galaxies and mergers with smaller galaxies. And here they're actually showing what their model galaxies look like, trying to show that they have somewhat realistic looking galaxies. And then here is an illustration from the simulation showing the ordinary matter falling into these dark matter wells. And so as it falls in, it can heat up and shock, and so that's why you have these this brighter orange-white emission everywhere. All right, so here is the one of the simulations, and what we're looking at is just a relatively small region of space. So we're not looking at the whole billion light-year wide box, but we're following just a handful or a couple handfuls of larger galaxies, and we're seeing the reddish stars, which are the older stars, and then but you can also see more whitish clumps, and those are the younger stars. And what is happening is that just like the earlier simulation that we saw, as galaxies merge and the gas from the two galaxies merge and together, that gas can provide the impetus to form the next generation of stars. And so you can see all these new stars forming in the spiral arms of this new galaxy as galaxies merge. And then there's also additional gas that's fallen in from intergalactic space. And now we're seeing two galaxies merging, one that was more of an elliptical, and you're seeing a new wave of star formation, hence all the blue stars there. These really small clumps are much smaller satellite galaxies. And then over time, what happens is, again, just like we saw in that merger between the Milky Way and Andromeda, you have sort of an elliptical galaxy with a big lump of reddish older stars and far fewer blue young stars. And so it's really neat to see how you can run simulations at vastly different scales. The first simulation that we saw, the Milky Way and Andromeda, focused only on the Milky Way and Andromeda. But here, we're looking at a simulation that looked at a much, much bigger volume of space, but you get more or less the same sort of results. So it seems like, if we do have a pretty good understanding of the physics that's involved, and so we feel pretty confident that, despite not completely figuring out all the little details, we have a pretty good understanding of how galaxies have evolved over the history of our universe.